Okay, so this is question number 8 of tutorial sheet 7 and how it should be solved. So first of all, I'll read out question 8 and then solve it. You can refer to your question number 8 in case you don't have the data that I'm looking at here. So question number 8 reads, a 50 kg child running at 3.0 meters per second jumps tangentially onto a stationary merry-go-round platform whose radius is 5.0 meters and whose moment of inertia is 25 kg meter squared. There is no friction. Find the angular velocity of the platform after the child has jumped on. So based on what we have read there's quite a number of things that we can see from there, and this here is some of the information that we have written down. The mass of the child is 50 kgs. The velocity of the child is 3.0 meters per second. The moment of inertia of the merry-go-round is 25 kg meter squared. And the radius of the merry-go-round is 5.0 meters. Now, when the question says that the child jumps tangentially onto the merry-go-round, what that means is the merry-go-round is circular like this. So that means that the child jumps tangentially. So the child is moving with the velocity and he jumps onto it tangentially like that. So that the velocity is the tangent. Now, once we have the velocity as the tangent there, then that's the tangential velocity. Tangential velocity is always related to angular velocity by the relation tangential velocity. Actually, that's the relation here. This one here. Or rather, let me just write it down. So that's tangential velocity is equals to omega multiplied by r. Okay, but what I'm doing here is I'm making omega the subject of the formula. So that means we divide both sides of this small equation over here by on both sides of the equation like that. So you see omega is now equal to Vt, which is tangential velocity over r. We know what the tangential velocity is, that's 3. We know the radius of the merry-go-round, that's 5. So we divide those two, that gives us a value of angular velocity, which is this here. So we now have a value for angular velocity of the child as he or she jumps onto the merry-go-round. Next is we can find the moment of inertia of the child. Now, when the child jumps onto the platform, let me just show that again. So this here is our the disc of the merry-go-round. Now, if the child jumps onto the circumference like this, then you will agree with me to say the radius there. We can use that radius there to find the moment of inertia, because that child now is going to be acting as though is the point mass on the circumference. Okay, so to do that, to find the moment of inertia of a point mass, we simply just use this expression here. Moment of inertia is equals to mass times radius squared. What is the mass of the child? 50. What is the radius of the merry-go-round? 5 squared. That gives us 25. 25 times 50, that ends up giving us moment of inertia equals to 1,250 kilograms meter squared. Now, if we want to solve for the angular velocity of the merry-go-round, we have to understand something here, and this is where the question is solved. So, just as the linear momentum of any collision is conserved, the angular momentum of any situation like this is also conserved. So we can therefore say the angular momentum, the initial angular momentum of the child, which is what I've written here. Okay, angular momentum, I is initial, C is for child. And then this is the angular momentum of the merry-go-round. That's why there's an M there, I for initial. So if we add these two, we find the initial angular momentum of the whole system. But then after the child jumps onto the merry-go-round, that is going to change. Okay, and so that must be equal to, because remember it's conserved, that must be equal to the final angular momentum of the child. That's why you can see F there for final, C for child, angular momentum, plus angular momentum final for the merry-go-round, like that. And then the formula for getting the angular momentum is the product of moment of inertia and angular velocity. So that's what you're looking at here. That's this. That's for the child initially. This is for the merry-go-round initially. This will be for the child finally, and this will be for the merry-go-round finally. Okay. So we know the moment of inertia of the child. We just replace there. That's 1,250. We know the angular velocity of the child. We found it as 0.6 right here. So that's why we replace them both here to find a value there. Now we know the angular moment, the moment of inertia of the merry-go-round is 25 as it was given in the question. But then the merry-go-round is not moving initially, so the velocity is 0. So we are multiplying 25 by 0, which is this here. Now on this other side here, we have this here, which is the sum of the angular momentum of the child and the angular momentum of the merry-go-round. Now, when the child jumps onto the merry-go-round, he or she spins with the merry-go-round. So that means they're going to be spinning at the same angular velocity. So we factor out this final angular velocity here. So you can see we have factored it out here. It's outside. Now we remain in the brackets with the angular momentum of the child, moment of inertia of the child, and moment of inertia of the merry-go-round. So when we work that out, now we have this. So we start from this side. So we start from this side here. This part here. 1,250 times 0.6 is 750, this. Okay, and then here we have factored this out. That means we have moment of inertia of the child plus moment of inertia of the merry-go-round. So when we add those two, we get 1,275. Then we just divide both sides of the equation by 1,275 to get the value of the angular speed of the whole system as 0.59 radians per second. And that's how we solve question number 8. Question number 9 is very similar to this. Again, let me read it out so that I can then refer to what we have written here to solve it. So question 9 says, you can refer to your tutorial sheet. It says a children's merry-go-round consisting of a uniform disc, so you have to underline that, disc, of mass 250 kgs is rotated at 25 revolutions per minute, so that's the angular speed, about the vertical axis of rotation. The radius of the disc is 5 meters. A says, if a 100 kg person sits at the edge of the disc, what is its new angular speed in revolutions per minute? Again, this is very similar to what we are just from doing here. But of course, the data given here is a bit different. So at this point, we have been given this as our merry-go-round. And we know this is initially rotating at 25 revolutions per minute. So that's the information which we have put here. The merry-go-round has a mass of 250 kgs. The angular velocity of the merry-go-round is 25 revolutions per minute. The radius is 5 meters, like that. And then in part A, we have now been given the mass of the person. This time it's a person, as 100 kg. And that's everything that we know about the person. And we know this person is not moving initially. So his or her initial speed is 0. That's tangential or angular. Then what we are simply doing now here is we want to find the moment of inertia of the merry-go-round. Since that's a disc, we find it using this formula here. If it's a disc or a cylinder, then you can find the moment of inertia by using the formula half mr squared. What is the mass of the merry-go-round? 250, that's what we've put there. What is the radius of the merry-go-round? 5, that's what we've put there. And so we work that out and get the moment of inertia equals to 3,125 kgs per meter per square, kg meter squared. Okay, so moment of inertia of the person, remember, The question has told us to say if that's the merry-go-round, this person is actually seated on the edge, like there. Okay, so that means if we take that person as a point object, then we can always find his or her moment of inertia, because we are simply just going to use the radius there as a point mass. So if it's a point mass, moment of inertia is equals to mr squared. What is the mass of the person? 100. That's what you see here. What is the radius if he's seated, or if he or she is seated on the edge? 5. So that's 5, and then we square it. That ends up giving us moment of inertia equals to 2500. Then we go back to our earlier concept. For something like this, its moment of inertia we know is going to be conserved. So that's this. Angular momentum initially is equals to angular momentum final. So here now what we are doing is we are saying this here is the angular momentum of the person initial. This is the angular momentum of the merry-go-round initial. This is the angular momentum of the person final. This is the angular momentum of the merry-go-round final. The person is not moving initially, so 0 is the speed times the moment of inertia, which is 2500. And then we know that the initial angular speed of the merry-go-round is 25. The moment of inertia, we just found it to be 3125. So we multiply those two values. We get 78,125. This side we have a 0. Now, when the person jumps onto the merry-go-round, the person and the merry-go-round spin together. Therefore, their final angular speed is going to be the same. So we factor that one out. That's why you see this one has been taken out of the equation. In the brackets now, we are remaining with the moment of inertia of the person and moment of inertia of the merry-go-round. Then we just replace. Moment of inertia of the person is 2500. Moment of inertia of the merry-go-round is 3125. Okay, so when we multiply that by omega f, we get 5625 omega f. That's equal to the other value we have on the other side, which is 78,125. Then we just divide both sides by that value, the 5625, and we end up with this here as our value in revolutions per minute. And that's how we find the final angular speed of this particular system here. Now, question 9 has a part B. Now, a part B is simply just the same as what we have done. So I expect that you can do that, but I'll just give you a hint. So this, in the first question, in part A, is our, that's our merry-go-round. So in part A, we're told that the person is seated at the edge like this, where we know the distance from the person to the center is just the same as the radius. Now in question 2, they want you to find the same speed, but now with the person seated 2 meters from the edge. So instead of the person being on the edge, now the person is here. Okay, 2 meters from the edge, meaning the distance between here and there is going to be 5, which is the radius, minus 2. That's 3. So now what it means is you are going to repeat everything we have done, except now this here is going to have a value of 3, it's going to have a value of 2, and it's also going to have a value of 1 when the person is seated 4 meters away from the edge of the merry-go-round. So you can try that one out, but actually the information given here, the solution is simply just going to be the same as this. Only we are just changing one value of radius there, and that's it. Okay, so for this one we are done.